But radiation and winds are not the only things coming from the sun. Tiny particles, neutrinos, stream out from the nuclear core. A byproduct of fusion, they are like the exhaust from an automobile that can tell us how the nuclear engine is running. Sudbury, Ontario. The Solar Neutrino Observatory. For 3 years, over a mile underground, they've excavated an enormous cabin 10 stories high. The heart of the detector where they hope to catch a few neutrinos is a gigantic water tank. If our eyes could see neutrinos, they'd rain down heavier than the worst blizzard imaginable. Nothing gets in their way. Passing through 1.25 miles of rock is nothing for these unstoppable particles. This experiment needs $300 million worth of heavy water. They use heavy water because it gives off a tiny flash of light when it's hit by a neutrino. And that flash is what they'll look for. Different nuclear reactions give out different types of neutrino. The sort of neutrino and their number are strong indicators about which reactions are taking place. No other experiment can tell us so much about the sun's core.
Well, there are about 100 billion neutrinos passing through the tip of my finger every second, and yet with 1,000 tons of heavy water, the best medium for detecting neutrinos, in our detector, only about once an hour does a neutrino stop and produce a burst of light that we observe. By going, in our case, 6,800 feet underground, we have a large depth of rock to shield cosmic rays from reaching our detector. Otherwise, if we put our detector on the surface of the Earth, it would glow like the northern lights.
Neutrino hunter Duncan Hepburn goes to work in a solar observatory where the sun will never shine. But as well as discovering the secrets of the sun's core, this experiment will also tell us about neutrinos themselves. Know that, and you're well on the way to knowing the ultimate destiny of the cosmos. The Neutrino Observatory needs to be a very clean machine.
Everything in the world is radioactive to some degree, a low level. And our only defense is to keep the place extremely clean so there's no dust in the middle of the detector.
This underground lab is cleaner than an operating room. Duncan needs to scrub out.
Everybody that comes in takes a shower. The basic mechanism for detecting a neutrino is it comes from the sun, through the earth, and into our heavy water.
Heavy water, but the hydrogen atoms in that water have an extra neutron. That extra neutron is the target. Strike it with a neutrino and a high-speed particle comes off.
Think of it as a billiard game, and suddenly we have one ball going very fast. It produces a forward-looking cone of blue light. Therefore, surrounding the heavy water is 10,000 light sensors that are tuned up to watch the blue light and count that. This forward cone of light indicates the direction the neutrino came from. That's a very valuable signal because we can always match that up with where we think the sun is in the sky at that time.
As well as divulging the secrets of the sun, the Sudbury experiment could tell us far, far more. The most fundamental question of science may be answered here. Sparkles in the water should reveal how much the neutrino weighs. Know that, and you can forecast the future of the universe.
There are more neutrinos than any other type of particle in the universe. If they have even a tiny mass, that can influence the current expansion that has been taking place since the original Big Bang, and perhaps even create a big crunch billions of years in the future.